All right, ladies and gentlemen, this week we're talking about bones or osseous tissue. So in chapter 4, we introduced the idea that bone is a type of connective tissue, right? But we're not only going to look at how bone functions in that role as a connective tissue, the cells, its matrix of collagen fibers and hydroxyapatite crystals, but also how the entire system of these bones, our osseous system or your skeletal system, functions for the body as a whole. So last week we were talking about the integumentary system, our skin, which covers basically our entire surface area that's interacting with our external environment. And our skeletal system makes up or takes up a lot of the volume of our internal environment inside of our body, providing the structure that all of our other tissues and systems are basically built upon and built around. So in this chapter, we're going to talk about the various types of bones, right? You've already been introduced to the specific names of individual bones as a part of our skeleton, but we do have some categories that we classify different bones as. We'll look at the cell types in bone because it is a connective tissue. We have cells and then the matrix. So we'll look at the cell types that make up bone and then what fills its matrix. We'll look even closer at specifically compact versus spongy bone, which just ends up in different arrangements with our other classified types of bones. The periosteum and endosteum, which are the membrane layers within our bone, and then how bone grows and how it functions as mineral regulation, as storage for minerals like calcium and phosphate and magnesium, and how we regulate that storage or access to those minerals by using bone. So our bones provide a variety of functions, besides just support for our body as the framework that our muscles pull upon. We store large amounts of calcium, phosphate, magnesium, and many other minerals in our bone, making up a majority of the mass of that bone as these hydroxyapatite crystals that we'll be talking about a lot today. But we also store a lot of our lipids there. So 80% of the fat in your body is right under your skin. And then the next largest percentage is in your yellow bone marrow in your bone. Another function of that bone marrow, of red bone marrow, is to produce a lot of our blood cells. And then bone is arranged in order to protect some of our more vital organs, such as the rib cage of our trunk, and provides leverage for our muscles to pull upon to allow us to move throughout our environment. So our major classification or types of bones is based off of shape. So we have some small categories where there's just a few bones in the human body that you might find as part of that shape. And then we have some of our larger categories where we're going to be spending most of our time. So some of the smaller categories would be like sutural bones or sesamoid bones. These sutural bones are those that are formed by essentially incomplete sutures. Right? We kind of introduced the idea of wormian bones as a part of the skull that may or may not be present depending on the individual. These are just tiny, oddly shaped bones that you would find in an incomplete suture, right? So instead of the suture forming a direct line between so it'd be our frontal and parietal bones here, they kind of went around, or ossification continued separate from that frontal and parietal bone, and so created this tiny sutural or wormian bone. Those names are synonymous. Sesamoid bones, would probably be our second smallest category, are just other oddly shaped bones that we don't really have a category of other bones that fit that shape. So they get their own category, the sesamoid. The most common would be the patella, forming that almost triangle looking shape. And there are a few others that may show up in like the hands and feet of different individuals. But these are also uncommon, or at least going to vary by the individual. And then our next two smallest categories would be the short bones and irregular bones. So short bones are just small and they're going to be spherical or cuboidal in shape, so like our carpals and tarsals. Irregular bones are really just describing mainly the bones of your vertebrae, your vertebral column. They have a lot of specific shape to them that does repeat throughout all of your vertebrae, but that's very unique compared to the rest of your bones. And then lastly, our two largest categories of bone types would be our flat bones, which, as they sound, are mainly flat in shape, and then our long bones, which end up being quite long, right? So our examples that we've been given here are our humerus for a long bone, so think femur, fibula and tibia, radius and ulna, right? Those are long bones. And then our flat bones, think like the bones of the skull, right? And so within all of these bones, we then have compact or spongy bone, depending on the organization of those cells, collagen and hydroxyapatite crystals of the matrix. And then all of these are just different organizations of that type. So flat bones are like a spongy bone sandwich, where we have compact bone on the outside, like the bread, and then spongy bone in the center. Long bones take that organization and manipulate it a little bit, where we have, again, compact bone, mainly surrounding all of the outer portions, and then different areas of spongy bone, making up various cavities for different types of bone marrow to fit into. And so we'll look at that organization through these other slides. And we're mainly going to focus on the structure of flat and long bones, since those are where we're seeing, what are making up a majority of the skeleton, and are great examples for looking at how those two types of bone function and how they're organized. So here's a closer look at those two major types. So we have our long bones, which, like I said, create some different cavities. We have our epiphyses at our ends, and then the diaphysis in the center. And so the diaphysis has this big open cavity that runs throughout the entire shaft, our marrow cavity. It's basically empty with a little bit of spongy bone in here. And so you just have a bunch of marrow filling up that space. And then the epiphyses are the cavities at the end that aren't just open cavity. They're mainly full up of spongy bone, with all these little trabeculi, these spindles that you can kind of see going throughout, filling up that space. And then there'd be marrow in between those trabeculi, in between that spongy bone. Flat bones don't have a large marrow cavity like our long bones do. Rather, they just have compact bone running around the entire perimeter, and then spongy bone filling up the space in between. And then similarly, there would be marrow, bone marrow in between all that spongy bone in that space. So again, bone is connective tissue. It is dense connective tissue. It doesn't have much of a liquid in its matrix. Its matrix is very, very solid. So we have our organic portion of the matrix, the space surrounding the cells in this connective tissue. The organic portion is mainly going to be collagen protein fibers. But a majority of the mass of our bones is inorganic. It is made up of minerals, these hydroxyapatite crystals. I know that's quite a mouthful, hydroxyapatite crystals. And those are our minerals, mainly calcium and phosphate, but we have lots of other minerals that make up that structure. And that's what makes up a majority of this space. So all the yellow that you see as we're looking at this bone is basically just hydroxyapatite crystals. And so throughout those crystals, we're going to have individual bone cells. So a mature bone cell is an osteocyte. Remember that pattern, this suffix cyte is referring to a mature cell. So osteo referring to bone, cyte referring to a mature cell, and osteocyte is a mature bone cell. These are going to be kind of packaged up in these lacunae. So they end up completely surrounded by the hydroxyapatite crystals and the collagen that they produce, which puts them into these little cavities, these lacunae. And they will have little extensions of their membrane to allow them to communicate with and transfer nutrients between other osteocytes. And those little canals, those extensions of the plasma membrane, are called canaliculi. So the word canal is directly in there, and they look like these little canals. You can see the other cells that they would be connecting to, the ends of those membranes from those two cells. But a majority of the space around them, again, is the matrix, collagen fibers, and mostly these minerals, these hydroxyapatite crystals. So we have four major cell types that you would find in bone. Of course, we have our mature bone cells, those osteocytes, packaged up in their little lacunae surrounded by the matrix. But those osteocytes are just mature osteoblasts, which are immature bone cells that are mainly there to secrete, make more bone. Okay? Osteoblast, a blast is typically referring to a stem cell. So osteoblast make more bone. Osteocytes are there to regulate and upkeep that bone. And so as an osteoblast is making more and more of that matrix, so it's secreting collagen and hydroxyapatite crystals around it, it's going to migrate closer towards the center of the bone and surround itself with that matrix. And that's how it ends up in these little lacunae. So blasts make more bone. Osteoprogenitors are the true stem cells of our bones here. They are just there to make more osteoblasts. So if you follow the development line from immature baby to all the way mature adult bone cell, we have our osteoprogenitors, which make more baby osteoblasts, which make more bone. And then those osteoblasts end up surrounded by the bone that they've made and are now mature osteocytes, which are there to upkeep the bone surrounding them. So all of these three cell types are there to essentially make more bone, right, and upkeep that bone. But our last cell type you would find in bone are osteoclasts. And these are much more like macrophages, and in fact are formed in marrow rather than coming from osteoprogenitors. And they form from the fusion of multiple macrophages, basically. And so you end up with this really large multinucleated cell that is there to break stuff down. And those are osteoclasts. So clasts break down, blasts make more. And just like macrophages, which destroy invaders, osteoclasts are going to break down bone. So it is the balance between osteoblasts making more bone and osteoclasts breaking apart that bone that ends up playing controlling, regulating the calcium balance or mineral balance in general, as far as what is available in our blood. If we have excess calcium traveling through our blood, osteoblasts can absorb that and then store it in bone, make more hydroxyapatite crystals. And then if we need access to more calcium, we have low levels in our blood, osteoclasts can break apart those hydroxyapatite crystals, release calcium back into the blood. Right? And that goes for all the minerals stored there, phosphate, magnesium, etc. If we need access to it, osteoclasts can break it down. But besides mineral balance, that back and forth between osteoclasts and osteoblasts is also going to play a role in recycling our bone in the same way that your cells are constantly replacing themselves, renewing that tissue over time. Osteoclasts are going to break apart bone so that osteoblasts can make new ones to refresh it. And this is how cartilage ends up being replaced by bone. A lot of your bones start out with a cartilage model, right? The same type of dense connective tissue that you can feel in your nose and your ears. So we start with cartilage forming the shape of what will eventually become bone. Osteoclasts come in and start breaking apart that cartilage, and osteoblasts replace it with bone. So it ends up being this bone tissue instead. So osteoclasts are also only our second example that we've seen of a multinucleate cell in the human body. So skeletal muscle cells and osteoclasts are the only cells that we'll talk about in this course in the human body that are multinucleated, so have more than one nucleus in one single cell. There is a third cell type that is part of our livers that also is multinucleate, but that makes up the only types of cells in the human body that would have more than one nucleus. So skeletal muscles, osteoclasts, and then cells of the liver. Okay. So we're first going to look at compact bone and how all of this stuff is organized in that compact bone. Because we see basically an example of all of our different structures shown, and then we'll look at how that is organized a bit differently for spongy bone. That's essentially it as far as our details, our structure and organization. So a single unit of compact bone is considered an osteon. You can see that kind of detailed with this line, but really if we follow that all the way around, it's this entire circular shape that would be considered one single osteon. Sorry, didn't mean to go forward. This is all one osteon. And you don't see osteons in spongy bone. The structure of the organization of the material is similar, but the higher level organization is different. So anyways, the name osteon is referring to compact bone, a single unit of compact bone. And what we get are these three layers, basically, of concentric lamellae, where we have collagen fibers organized in this parallel formation, similar to the tension lines that we saw in skin, where collagen ends up parallel in these different directions. These concentric lamellae have parallel collagen fibers that end up going in different directions within each layer. We'll take a closer look at that later. And then within these layers, we have various osteocytes within their lacunae, which you can see as these black holes here. That would be osteocytes. They have their canaliculi. These little black lines you see are their plasma membrane extensions, so they can communicate and diffuse and absorb materials with neighboring osteocytes. And then, of course, a majority of that mass is the hydroxyapatite crystals. But all these big white spaces in the center of each of our osteons are called central canals. And those are open spaces that allow for blood vessels and nerves to travel throughout the blood. So central canals, concentric lamellae surrounding those central canals, and then one full unit where they all are surrounding one central canal that is an osteon. So osteons surround one central canal with concentric lamellae. Within those lamellae, we have osteocytes holed up in their lacunae, and then hydroxyapatite crystals making up a majority of that structure. So here's another look at that. Right? So this would be dead bone that has lost most of its organic fiber. So like the bone that we have in our lab, right? It's very light because all that's left is the hydroxyapatite crystal, the minerals. Because all the living stuff, all the organic matter, the cells and the collagen fibers have deteriorated and rotted and broken away, and there's no blood vessels filling up these central canals. So you can see those lacunae that are left behind. You can kind of see the strands where some collagen fibers would be, and then of course the central canal where blood vessels and nerves would have traveled through. And so in an osteon, right, you can see this organization a little bit better with our blood vessels shown within that central canal. Here, this innermost layer, this is a membrane called endosteum, and that's where you would mainly find your osteoprogenitor cells. So these osteoprogenitors are producing osteoblasts, which are going to start producing more of that matrix and push more into the center of the bone tissue itself, so away from the membrane, away from the outer lining, as they become surrounded by that matrix until they are now mature osteocytes. And you can see also that it's like three-layer structure that I was referring to before. We get 3 layers of concentric lamellae, which are going to have collagen fibers organized in different orientations. So each layer has their collagen fibers parallel, right? This line of collagen is parallel to this line of collagen is parallel to this line. But the next layer of the lamellae has them in an opposite direction. So where these were top left to bottom right, these ones are top right to bottom left. So we get them perpendicular throughout these layers, which allows the bone to resist force from multiple directions. Hydroxyapatite crystals are what resist our compressive force, so like the weight pushing down on our bone that would try to shorten it in both, so from either direction, coming up to compressive force is kind of pushing towards the center in that way. But these collagen fibers are what are resisting force in other directions. So resisting the tensile force, which would be kind of pulling the bone apart. So as our muscles are working against each other or causing forces to pull against each other, these collagen fibers are resisting that pull away from the center. And they also resist shear force, which is sideways force. Okay? And of course, we need our bones to be structurally stable as they are providing the framework for the rest of our body to build upon. So collagen resisting that tensile and shear force side to side, and then hydroxyapatite crystals resisting that compressive force. So you can see that described here. So compressive, pushing towards that center, that's resisted by those crystals, those minerals. Tensile force pulling away from the center, and then shear force going side to side, those are all resisted by collagen fibers. You can kind of see how that weight gets distributed throughout a long bone here, through that compact bone. So surrounding your compact bone, we have two different membranes. And we already introduced the endosteum a bit, but we'll look at that again. So we have our periosteum. That suffix steum is going to show up a lot as these connective tissue membrane layers surrounding these larger structures. So when you see steum or eum, that's referring to these membranes. So an osteum is a bone membrane, and then peri is around. Or I guess in some of our later tissues, you're going to see peri as the middle membrane. But we'll get to that later. So the periosteum is the outermost membrane in our compact bone. It's surrounding the outer portion, the circumference of your compact bone. And this has lots of smaller blood vessels and nerves and your osteoprogenitor cells there to make more bone. So this is blood supply and more bone cells, essentially. This also ends up becoming continuous with some other fibers or some other connective tissue layers like those of tendons and ligaments. And then our inner membrane is our endosteum. So this is what was surrounding those central canals. You saw the inner membrane. And so similarly, have some osteoprogenitor cells, have lots of our bone cell types there, but we don't have as many of those tiny blood vessels and nerve endings since we have the central canal going through it. So you can see that organization a bit better here. So there is the periosteum going around the circumference. And then surrounding these central canals, we have endosteum. And I believe these other white layers would also be considered endosteum. Don't hold me to that. So you can see each of our osteons, that single unit of compact bone with 3 layers of concentric lamellae. You do also have circumferential, sorry, that's a tough word, circumferential lamellae, just under or just deep to the periosteum, which is creating layers that would go around the entire circumference of that long bone or compact bone in some cases. At least circumferential lamellae. But these concentric lamellae and interstitial lamellae are just part of compact bone. And that's what makes those opposite layers, opposite directions, these parallel spirals of collagen. That comes from concentric lamellae. But we also have a different type of bone, right? That's all been focused on compact bone, which as it sounds is much more dense and compact as far as the actual bone tissue making up that structure. But we also have spongy bone. And the name spongy comes more from how it looks visually rather than the actual characteristic of the bone, because it is still brittle, just like it is mainly minerals and collagen fibers. So it is brittle bone. But it makes this more spongy looking shape because we have essentially an osteon that instead of being surrounded by other osteons is creating these branches that we call trabeculae. So each of these little branches are trabeculae, and then the organization of the material of the bone within those trabeculae is very similar. But this provides space for more bone marrow. So most of the inner spaces within our long and compact bones, or within our long and flat bones, is going to be full up of spongy bone, so that there is space for bone marrow, yellow and red bone marrow. So you can see that organization here. So here looking at the epiphysis, the outer sections of a long bone, we have a whole bunch of spongy bone filling up that space with bone marrow in between, all this red. And if we take a closer look at a single trabeculae, we see that it looks a lot like an osteon. We've got osteocytes in their little lacunae with canaliculi, allowing them to communicate and diffuse materials with neighboring osteocytes. But most of the structure is still hydroxyapatite crystals and collagen fibers. We just don't have a central canal in this case for blood supply and nerves. There's another look at the same thing. And then here's spongy bone without the organic material. Okay. So that's where I'll stop this video, and then I'll record one more going over ossification, which is the formation of new bone or bone growth, and how our bones play a role in mineral regulation for the body. So I'll see you in the next one.